Hello everyone, I am Jinyang. In this video, I'll be sharing with you my final year project titled Automatic Recognition of Facial Expressions. For this presentation, I'll first introduce to you the field of automated facial expression recognition, describe the common challenges faced by researchers, and what our project has set out to achieve. Next, I'll take you through our model architecture and how the different components play a critical role towards ensuring the success of a model. Then, I'll present to you our results, evaluated on the RAF-DB dataset, and how a model performs as compared to prior art. And finally, I'll demonstrate to you our working prototype, which comes in the form of a Flask web application with a model integrated into the app. It has been found by scientific research that in human communication, 55% of the information is exchanged non-verbally, and facial expression, naturally, acts as a direct and fundamental social signal. Over the past few decades, with GPU performance growing drastically, computer-based facial expression recognition systems have taken off and have seen a wide range of applications, from retail to medicine to police work. And as we try to design more powerful FER systems, two challenges prop up. One, it is commonly observed that existing FER systems consistently outperform on some expression classes like happy, while underperforming on other classes like disgust. Second, due to a lack of alternative options to boost performance, network backbones of increasing complexity are used, resulting in extremely sophisticated networks going up to hundreds of millions of parameters. Hence, it is the goal of our project to create a FR model that is accurate at identifying facial expressions with robust performance across different types of expressions, while remaining lightweight with minimal number of parameters, and efficient with minimal amount of floating point operations required to compute the result. Moving on to model architecture, this is how our overall architecture looks like. Let me take you through portion by portion. We chose to start off with a ResNet 18 backbone, pre-trained on the ImageNet, for two main considerations. One, the ResNet 18 backbone is small, with just 11 million trainable parameters, as compared to Exception's 23 million and VGG16's 138 million. Second, ResNet 18 is powerful, as it is designed to circumvent the same signal degradation problem faced by non-residual networks. Next, we move on to the novel feature interaction block, which is inspired by how CNN abstracts lower-level features into higher-level features. Here, we directly aggregate higher-level abstractions in groups of K, because keep in mind, no feature is dedicated to a single facial expression, but rather, we are looking at the entire set of features to deduce the most likely expression. So by aggregating these features into groups, we let contradicting feature abstractions neutralize each other, while retaining the strength of agreeing feature abstractions. We experimented with different values of K and found the optimal value to be 2. Moving to the sharing affinity block, this is driven by three main equations. For every batch of images, we take the average of the feature maps to come up with a batch expression, and then use it to update our moving average generic expression. Then, we try to break down every expression into two constituent parts, the generic part and the unique part. To explain this in an easy-to-understand manner, it is akin to teaching the machine to recognize different facial expressions by understanding how these expressions should look different from others, rather than these machines learning each type of facial expression from scratch. And last but not least, let's talk about our choice of the loss function. Here, we use the additive angular margin loss. While you can find the exact equations in my report, the underlying intuition is that we want each of our clusters to be as tight as possible while maximizing the distance between different clusters. So for every prediction, it is more likely for us to find it closer to the correct cluster because the wrong clusters are further away. And the use of a margin lets us do precisely that. Finally, let us see how our model performance compares to the other state-of-the-art techniques. Here we chose the RAFDB because its images are taken outside the lab environment, which is realistic. Second, it is a dataset that is commonly used by FER research to report performance metrics. This facilitates comparison. And as you can see, our final model performs better than all prior art in terms of accuracy, robustness, lightweight, and efficiency. To conclude my presentation, let me walk you through my web app prototype. Let's go. Our prototype has three main functionalities: FER in images, FER in videos, and live FER using webcam as an input stream. For FER in images, we can input the directory where images are located. And once our model processes and annotates these images, they'll be saved to the output directory and also displayed in our app. For FER in videos, we can input the video file path and we can start watching the processed stream almost right away.
Elon, thanks for being here. With your background in payment systems, you understand the important role of...
This is due to a watch as we process trick outlined in our report. For FER in webcam, we can use the web camera as an input stream of images and process each image before fetching a new one. With that, we have come to the end of our presentation. Thank you for your time, and we hope you enjoyed watching our video.